Welcome to the second lecture video in our Class 11 times series of videos. We ended the first video with a discussion of Fisher projections. So one of the expectations for this course is that you must be able to convert bond line structures to Fisher projections and vice versa. We'll get a little more practice in this in a future video. But first I wanted to go back and consider some bond line stereoisomers and relations between them. So first let's consider a molecule with two stereocenters. If the substitution is not identical, there are going to be a total of 4 possible stereoisomers. So let's consider RR 3-chloro-2-hydroxybutane, this molecule here. If there's an RR stereoisomer, its mirror image, or enantiomer, which is going to be non-superimposable, so not identical, is the SS configuration, so this molecule. And you can see how it really does look like a mirror image of the RR configuration. It looks like it's looking at itself in the mirror. So we know these are related as enantiomers. Well, if there's an RR configuration, then you could also think about an RS configuration for this molecule. So what about RS 3-chloro-2-butanol, this guy? Well, it is a diastereomer of both the RR and the SS configuration. That's why I have diastereomers written for these arrows that conjoin pairs of stereoisomers. So all of these arrows are relating pairs of diastereomers. So what is a diastereomer? A diastereomer is a stereoisomer not related as an enantiomer. Well, to know the definition of diastereomer, you have to remember what the definition of stereoisomer is. A stereoisomer is an atom or a molecule whose atoms have the same connectivity. And of course, an enantiomer is a non-superimposable mirror image. So basically a diastereomer is simply a molecule whose atoms have the same connectivity but is not related as a non-superimposable mirror image. So, of course, the RS 3-chloro-2-butanol also has an enantiomer, and that would be the SR 3-chloro-2-butanol. So those are non-superimposable mirror images. So, what shall we do next? We shall consider molecules that have identical substitution and see what effect that has. So you must be careful because two identically substituted stereocenters give rise to only 3 stereoisomers. So let's consider RR23-dibromobutane, this molecule. The mirror image of the RR configuration is the SS enantiomer. So we know that this is the enantiomer. These are not identical molecules. They're non-superimposable mirror images. If you have an RR configuration, you could also have an RS configuration. So what do I mean by identical substitution? I mean each stereocenter has the same groups. It has a bromine, a hydrogen, a methyl group, and then a 1-bromoethyl group. So now, when we try to take this diastereomer of the RR and create a non-superimposable mirror image, it may look like it's non-superimposable, but this mirror image is really identical to this molecule. And so that brings up this notion of meso compounds. So what we also mean to say when we see a mirror image of a molecule that is identical, we mean to say that this molecule is achiral. So a meso compound is a small subset of a larger group of achiral compounds, which is a compound that has two or more stereocenters, but that is superimposable on its mirror image, which is to say it's identical. And that's another way of saying it is achiral. So, I guess I'm going to try to prove to you on two-dimensional paper that those molecules really are superimposable, and I might, have some help from a molecular model to get a more three-dimensional sense. Many of you will be able to see this. You can see that, it doesn't look like, this molecule will be able to superimpose, at least if you flip it over in a, rotating around a vertical axis, 180 degrees. However, if you do draw a horizontal axis and rotate around that 180 degrees for this molecule, you get this one. You haven't broken any bonds or changed that molecule, but you can see how this molecule is identical with this one, which means it's superimposable. Meso compounds, as I've alluded to, are achiral, which means you should be able to find a plane of symmetry, an internal plane of symmetry in them. And indeed, if you take your RS configuration and you rotate around this carbon-carbon single bond a certain number of degrees, you will arrive at a configuration of this 2,3-dibromobutane where you can clearly see that there is an internal plane of symmetry. So I think I'll finish this talk with just looking at molecular models to try to convince you that this is true. So there is a molecular model of RS-2,3-dibromobutane, and I think you would agree that I have constructed its mirror image. And this is something you can do with your molecular models as well. I think you will have enough carbon atoms and hydrogen atoms, and then atoms that you can treat as bromines or symbolize as bromines. So what I'm saying is, if we simply rotate this 180 degrees around a horizontal axis, now you can probably see that you could superimpose the molecule on the right with the molecule on the left. So they are indeed identical. And if they're identical, then we only need one of them for demonstration purposes. And like I said, you could rotate around the middle carbon to arrive at a configuration that you can clearly see has an internal plane of symmetry, cutting right down the middle of the molecule vertically in this representation. All right, so that is the end of this video.